good evening, minions. Once again, hi. I hope you're having a great day. My name is Nathan. I am a PhD student. I am a few months away from graduating. I hope. I need. Um, and yeah, I'm here to do a bit of chemistry, talk about how I do it, because I'm a great big nerd and I really like doing this stuff. Um, now, uh, there was that was yesterday. So I was having a little kind of impromptu meeting with my professor, and for various reasons, but mostly because I'm perpetually tired. But uh, particularly tired yesterday, crappy sleep, all that stuff wasn't just not my day. Um, which it happens. We all have those, and it's okay. Um, but like while we were talking about various things, uh, I said a bunch of things that that just have haunted me since. Because I'm like, wow, that sounded pretty stupid, huh? And yeah, and I mean it's not the first time. I and it won't be the last. Um, but it's really frustrating when that happens, and like it's not at all as if I'm a dummy. I do not think poorly of myself in that regard, but yeah, it's tough not to have some pretty negative self-talk when things like that happen. And as I said, I've got a lot of experience with that feeling. Um, I mean, I've been in university for 12 years, 12 and a half almost, and it doesn't get a whole lot better, that feeling. And the imposter syndrome was raging hard after that happened. Um, and so I guess what I'm getting at is that, ooh, hey, captions, hello. Um, so just that when this happens to you, because this happens to everybody, um, just keep in mind that it is not at all a reflection of how smart you are. It is not a reflection of your quality as a student or as a person. Um, and so it may suck for a while. And it's okay to be frustrated and to sit with that for a while. But um, just remember that it's saying silly things does not make you a silly person. Saying stupid things does not make you a stupid person. I've taught several. Hello, it's lovely to see you, Cheesiest of Cakes. Welcome, welcome. I was just talking. I'll catch you up a bit. So I was just having a little ponder about yesterday. I was having a bit of an impromptu meeting with my professor, and we got talking about stuff that I wasn't super prepared to talk about. But I was fully in a people pleasing mood, and so we just went and had this conversation, and I I put on full display my inadequate understanding of what we were talking about, and so just talking about like it's a bad feeling. It's not great, and like it's far from the first time. It's not going to be the last. But just that, like this is a thing that happens to absolutely everybody. Even if you were a PhD student who's been studying this stuff for 12 years, this stuff will still happen. You may have an off day. Yesterday was my off day, and it felt pretty crappy. But it is important to, well, first of all, to acknowledge those feelings and sit with it for a bit, and just remind yourself that it is not a reflection on you as a person. It doesn't mean that you're stupid. And the imposter syndrome bubbles up in those moments, and it's tough to deal with, and it's a thing that we deal with and we get through. And either way, you're awesome. Never forget that. Thank you so much. That's really kind of you to say. And for the record, I think you are awesome, and I hope you don't forget that. Because at some point, like I was saying, like this is a thing that happens to everyone. This is a feeling that everybody gets sometimes. And I've been teaching undergraduates for about 8 years now, and I know I am fully aware that some of them have felt that way when they have talked to me about this stuff, and I can promise you that when this has happened, I have never ever thought any less of a student for saying something like that. For being incorrect about something, for having an understanding that was not equal to mine about something. Never have judged anybody for that, and I certainly hope I never will. So yeah, it is not an indication of the quality of a student or of a person. For a prime example. There's one student in particular who gave me just a report that was it wasn't good. it was pretty bad. They said some things that were blatantly wrong. It didn't get a great mark. Well, we talked about this later. We talked about so here's what appears to be the gaps in your understanding. So let's work on this. Let's talk it through. And let me tell you, this person is one of the smartest people I have ever met, and he is still a very good friend of mine. He was just down a couple weekends ago for a visit, and he is so much smarter than me, and just very articulate. But when he was making that report, he probably just had an off day, and he said some silly things, and it had no impact on what an amazing student he was and how smart he is. So yeah, those things, they'll happen. It'll feel bad, and it's okay that it feels bad, because that's not who you are. All right, so with that out of the way, because I like to sometimes just ramble on if there's something on my mind, and that was on my mind. I definitely I was home at a reasonable time. I wasn't there terribly late, and once I got home, it was full on self-care evening, because it felt pretty bad. But we take time, be kind and gentle with yourself, and yeah, you get through it. Needed message. Also interesting to realize it happens to you at the PhD level. Absolutely. Yeah. No. Absolutely. It's also definitely something I wonder about, because when I was an undergrad, you talk to a PhD student, and it's like, my God. Like these people probably know everything, and then you get you get into a PhD and you talk through the stuff, and it's like, oh God, I don't know anything. Yeah, it is constant. It is imposter syndrome is ever present. But yeah, imposter syndrome is full of lies, and but yeah, the anxiety about that kind of stuff is it is absolutely just as present in a PhD as it is in high school, undergrad, any level. Yeah, we are at the end of the day people. We are primates with anxiety. Uh, but that part doesn't go away. But yeah, how you doing, cheesy soup cakes? It's right. It's a good one. I think I might have stolen that from some internet meme or possibly Forrest Valkai, who is like my absolute favorite science communicator. Really cool dude and incredibly smart guy. But yeah, tell me, Jesus Cakes, how are you doing? How's your weekend? I am very happy that you're here once again. It is always a good time. All right. And while you're working on that, I just wanted to put it out there that I was talking to my partner the other day, and I was talking about what I'd mentioned on Friday about like I would like to do like some more kind of like targeted, almost lecture like things. Hello, Tian. Having a lovely evening. Doing great. Made some improvements in my art and guitar stuff. Got into rotational dynamics, which is fun. That's awesome. I have so many questions already. What kind of art do you do? I'd love to hear all about that. Guitar stuff. What kind of guitar do you play? And how long you been doing it for? And rotational dynamics. My goodness, that's a heavy chunk to chew off. Is that for physics or just out of interest? I was doing a little bit of rotational mechanics myself. Well, kind of, sort of. Uh, uh, Nuclear dynamics, anyways. So this is that understanding NMR spectroscopy book that I'd mentioned last week. And so I was going through a bit of that and just kind of brushing up on the fundamentals of NMR, which has a ton to do with like well angular momenta and just molecular dynamics. Graphite portraits, nice. Learned some wood carving and clay sculpting. That's incredible. I love that. Yeah, my partner did a lot of woodworking when they were younger. Made some really beautiful stuff. Yeah, graphite portraits. That's amazing. What kind of stuff do you like to draw, or make portraits of? Guitar, total newbie, still trying to practice. Fair enough. I mean that's where you start. Because I mean, being a complete newbie at something is the first step to being kind of sort of good at something. So that's really awesome that you're getting that going. Also, thank you for the textbook. Yeah, absolutely. For AP Phys. Yeah. Yep. Very fun. Yeah. What am I thinking? Sorry. Traffic jam in my brain for just a minute. Yeah. Nice. Very cool. We'll do mostly random people, though a lot is musicians I like. Awesome. I love that. That's really cool. I always really like. I really enjoy hearing about the kind of art that people do or seeing it, because I have I have no artistic talent of my own. I couldn't draw to save my life. I do play saxophone, kind of, sort of. I mean, I played it for a bunch of years, and I think it's been about It's probably been about 10 years since I like really played it consistently. So that's kind of fallen out of it, but that's okay. Um, but yeah, so I always I like to live vicariously through people who can do artsy stuff. Like my partner, they're a really good artist, and it's lovely. Taxes work seem tedious. Yeah, taxes are tedious. That is accurate. Um, yeah, saxophone. Yeah, saxophone. Like the fingering patterns are pretty easy. Yeah, the hardest part is the embouchure, just how you hold your mouth and like how tight you hold it and the tonguing and yeah, that's the hardest part. um, but yeah, yeah. Yeah, I've often suspected that the reason I am completely ass at drawing is I have near total aphantasia, which means that I cannot, or I have a great deal of difficulty like forming images in my head. It's like I've talked to people who like when they're reading a book, they say like it's just like a slideshow or like they can see what's going on in the book in their head. Not me, not in the least. I see words on a page, and that's all I get. But that's just the way it goes, I suppose. But Daphne, hi, meow. Hi, are you going to come up and say hi? You're cold. Why are you cold? Oh, that's fascinating. So like on entirely the other end of the scale. That's wild. Yeah, no, like for a lot of years, I walked back and forth from university. It was about a 20-minute walk, so not too bad. And uh, excuse me. And very most of the time, I while I was walking, I'd be reading a book. And just like walking and reading all at the same time. And I got so many comments from people being like, "I don't understand how you can do that. How do you not walk into things? That's crazy." And I never understood because I'm just like, it ain't that hard. I just because I can still see everything that's going on. I just pay attention to it occasionally. Um, it was much later. It was maybe like 2-3 years ago that I learned that aphantasia is a thing, and like okay, yeah, that makes sense now. Because yeah, other people have images in their heads that pop up, and I have nothing. But that's yeah. Alrighty. Oh right, I was going to say so. Yeah, so last week I mentioned that at some point, yeah, probably fairly soon-ish, do I have an inner monologue? Yes, I do. Um, yeah, and I've heard some people say that their inner monologue is uh, not in their voice, but I do have it in my own voice. Like it's um, yeah, yeah. So I guess the short answer here is yes. Like I do have like my inner monologue when I think I think in I guess just my voice, I suppose. Um, yeah, yeah, yeah. How about you? Do you have any running commentary in your head? Oh, must make public speaking a breeze, huh? Oh man, wild, wild. that must be that must be an interesting time. Very chaotic office space. Fair. Yeah. Um, yeah. My mind is usually pretty quiet because it's really just one voice in there generally. Um, although the just raging tinnitus or tinnitus, I don't know how you say it. It's either tinnitus or tinnitus. Hello, buddy. You okay? Just a second. Oh dear. Aww. Well, maybe don't eat so fast, sweetie. Sorry, Daphne just just walked up in front of me and just had a little pukey. Yo, poor thing. Yeah, she just. Oh, sweetie. Oh, that's Oh, that one's gonna be harder to clean up. Oh dear. You doing okay now? If you didn't puke on anything important. Yeah, no, she's doing fine. She just her food dish is over there, and she clearly just ate too fast. It happens occasionally. Oh God, that's disgusting. Okay, that's a problem for future Nathan. We're not going to worry about that right now. Great. Yeah. Right. So I was going to say. So yeah, last week I mentioned I want to do some streams that are like a little more targeted, like not quite a full on lecture or anything. But ow. Why doesn't this work? Sorry, hair is inconvenient sometimes. So yeah, like I want to do something like not quite a lecture, but a little bit more focused streams on like NMR. I like really go over some of the theory of it and how to approach NMR problems and use it in more or less how you would use it in doing research. So I want to do that at some point. It's a fairly big undertaking, so it's not going to be like next week or anything, but probably in the next couple months or so. But in the meantime, what I might try fairly soon, like maybe in a couple weeks or so, is I've got a set of lectures that I made on a different topic. It's called crystal field theory. It's a really important and I think a really cool topic in inorganic chemistry that will definitely take some time to go through. And yeah, I've got all my slides are made for that already, so it'll be a lot less work to put that together. And it's just a really cool area that I would enjoy going over. So I'm going to subject you all to that at some point, fairly soon. But yeah, I feel like I probably still want to do mostly these kind of tutoring style streams, and just kind of like do this where I just talk about whatever occurs to me at the time. Ooh, rainbows, nice. But yeah, so that's something that we'll do. Don't go cold. Hi. Yeah. You doing okay? Are you feeling better, my sweetheart? Yeah. Good. Okay, so with that, gosh, I've been at this for half an hour and I haven't actually done any chemistry yet, so I could probably do a little bit of that. Okay, so last time we finished up this question about naming these compounds and just going over how we do that, which once again, very briefly, it just involves identifying the principal carbon chain, which is just the longest continuous chain of carbons, And then you identify your substituents and the carbon that they are attached to, and then arrange the name that results from those in alphabetical order by the first letter of the substituent, not the prefixes, but always the substituent itself. And then after that, after that, I think we went into yes, this one. We're talking about a little bit about vibrational energies and 0-point energies, cool stuff like that I'm not going to belabor here. And then we were talking about Newman projections, just kind of a different way of looking at hydrocarbon chains and looking at the different the different energies that are associated with different conformations based on the steric interactions between substituents on each carbon. And what I mean by steric interactions is just the electrons that surround each of these groups, because there's always electrons surrounding each of the atoms. They can interact over like fairly considerable distances, like longer than you might think, because these all exists in kind of what's often called like an electron cloud around the atoms, and those have a bit of reach. They can interact with other electron clouds, and so the way that everybody is happiest is by spreading out the electron density as much as possible, so that we minimize electron repulsion. Which again, it's the guiding principle of like 95% of chemistry, is just like always what we're trying to do is minimize electron repulsion. And so for that reason, molecules like these ones, I'm just going to erase these so it's a little easier to see. So yeah, molecules like these ones, I'm going to get a little closer here for you. These are in an eclipsed conformation, and so those substituents basically are interacting as closely as they possibly can. Yeah, there's my thing. So, and again, this is just a really basic representation of what this looks like, and so if they're eclipsed, then there we go. Then they're set up like this. So these groups and these groups and these groups are as close to each other as they can be in this format, and that is the least good way that they can be arranged, because if possible, we always want to have a staggered conformation, because that spreads out the electron clouds of these substituents. So next we're going to go in the opposite direction, and we use a line structure in order to create a Newman projection. And for that, I just want to grab a bunch of balls. And yes, I realize how that sounded. That was on purpose. Haha. There we go. Okay, that should be enough. Okay, so once again, what we're going to do is first I'm going to redraw this. So imagine this is your eyeball, and you are looking directly down this carbon-carbon bond here. I just want to see if I can draw a straight line. Not really, but close enough. Okay, so if we're looking at this molecule from this direction, then I'm going to use my model kit to make this much easier for myself. So let me turn the vibration off on my phone, so that is less distracting. Okay, so making a Newman projection out of a line structure is really it's easier. This is the easier direction to go in, because so we can just build up this molecule from the groups that were shown here. So again, when these are drawn out this way, so go away, Han Solo. So bonds that are drawn this way are those ones are in the plane of the screen. So so those are just kind of like as it appears. So these are well, I don't know how I can rephrase that. These carbons would be in the plane of the screen you're looking at, or the board that you're drawing on, or whichever. Bonds that are like this, these are called wedge bonds. And what wedge bonds indicate is that bond, or the atom on the end of that bond is coming out of the screen towards you. And then the dashed bonds are similar, but they're going out of the screen away from you. So yeah, dash bonds are going away from you, wedge bonds are coming towards you, and normal bonds, I guess, are just flat against the screen. So if we take that principle, I'm actually just going to draw this out towards you, away from you. I'm just going to say these ones are flat. Just like the Earth, right? Yes. Yes. Okay. All right. Okay. So, when we're looking at this molecule, so what I'm going to do is I'm just going to hold my molecular, or my little model of this molecule. I'm going to hold this up in front of me, and so I see there is an OH. So I'm going to circle that one in red. So that one is it's going to be on my left side, and it's coming towards me. So I put a little red sphere on the one that is on my left, and the one that and on the bond that's coming towards me. And then there is a hydrogen on the dash bond, so the one that's going away from me. And I can't really adequately circle that one in white, but here's my little hydrogen atom. And so this one I'm going to put on it's going to be attached to the same carbon, but now the hydrogen is going away from me. And then there's a methyl group on the other one, the one that is flat in that plane, and so that one goes here. Now on the other side, we've got a methyl group on the flat bond, and so I'm going to put that one here, if I can actually get this onto the model kit. Yes, very good. Okay, so that's what it looks like so far. And then hydrogens on both of the other two bonds. Yes, I've got another one. Very good. Okay, So I'll hold this up here for myself just to double check that I've done everything right. I've got on the carbon on the left, I've got oxygen coming towards me, hydrogen going away, and methyl group in the plane. On the right hand carbon, I've got a methyl group in the plane, and I've got two hydrogens on the other bonds. So very good. This model is now accurate to what this molecule is on the page. And so now, in order to make this a Newman projection, what I'm going to do is I'm going to now take the perspective of this eyeball, and I'm going to draw the Newman projection. So what I do first, I'm just going to draw the outline of a Newman projection because that is always going to be the same. So like that, and then like that, and then I just put little ticks here to say like this is where I'm going to be attaching the substituents. Okay, so there's my just template for a Newman projection. So now just make sure that these are still in the right place, and now all that I need to do is turn it so that now my eyeball, how can I, yeah, I'll do it this way so you can kind of see that from the right perspective. So now looking at it down this bond, I've got my oxygen is over here, my methyl group is up here, and my hydrogen, I'm just going to make that purple because drawing it in white would not do much good. And then, okay, so I'm going to hold that up for you to see. Let me just get the angle right. There we go. Pretty good. Okay, so hopefully that looks, that convincingly looks like the same thing that I've drawn. And just remember that this, so these lines represent the carbon that is in front. So that'll be this carbon here. And the line in the back, I'm going to make that pink, because pink is a great color. Oops. And so that is this carbon here. And so so continuing on, so looking down this, then this is, so that, whoop, wrong color. So this one is the methyl group, and the hydrogens are on the other two. Okay. So hopefully that way. Hopefully that looks like that to you. And well, if it doesn't, well, I'm right. So, so yeah. So this is like definitely the easiest way to make a Newman projection out of a line drawing. It is definitely kind of on the time-consuming side to do it this way, but it is certainly the easiest, and it's going to be the most consistently accurate way to do it, and it's a great way to just double-check your work. So like, you know, it's kind of hoped that like once you do this a bunch of times, you may not need to make a model kit. But like, I wouldn't stress trying to get to that point, because that comes with time and with practice. So yeah, when you're starting out, don't, I always recommend like don't take shortcuts, because when you take shortcuts, you can very easily miss important parts of the process if you don't fully understand the process. So yeah, like if I was doing this, I could very reliably reproduce a Newman projection just from this. I don't need to make a model kit. I could just do it. But that is because I have done this a bajillion times. And like this stuff really makes good sense to me. Because I understand exactly what I'm being shown and what I'm trying to do with it. So yeah, that's alrighty. Okay, so let's do this one. Right. Okay, so I'm gonna make you are gonna be a red carbon, and you're gonna be a black carbon, because that's the colors of my model kit. I'm going to have no. I'm going to have a purple eye this time. Okay, so let's do it from this perspective this time. Doop. Okay, so for this one, once again. Okay, so on the red carbon, I've got on this molecule there is a bromine coming towards me. Let's make you. Oh, what colors do I got? All right, we're gonna keep those as red. I need a fourth color, don't I? Yes, I do. Ha! I got a blue. Okay, so we're gonna go blue for bromine, red for the chlorine, and green for the methyl group, and again white for the hydrogens. Okay, so when I hold this model up, I've got a bromine coming towards me. I've got a methyl group going away from me. And I've got a hydrogen in the plane of the screen. So, just like that. At least for me. Now, on the other one, so, I've got a chlorine coming towards me, and then I've got two hydrogens. There we go. Okay, so. Alright, so that's what it looks like to me. Whoop. There we go. There we go. Okay, it looks like that. And it looks like that. So, now, hold this up so that it's... Just a second. I need to actually orient myself properly. Okay, like that. Oh, that's why. These are just drawn at a weird angle. That's okay. Okay. Oh, I see what they're doing. I think they're saying that this is in a staggered conformation, but that in a staggered, in an eclipsed conformation. They've drawn this kind of weird, and I'll show you why I'm being thrown for just a little bit of a loop here. So I'm just going to erase this. We don't really need that very much. Yeah, it's like on this one they've got wedge bond going down, and this one they got wedge bond going up, and this one they've got wedge bond going down and wedge bond going down, and so that just threw me for a little bit of a loop. I think they're trying to indicate that it's in an eclipsed conformation, but I think that's silly because there's no reason to put it in an eclipsed conformation because that's not how you would find it just out in the wild. Like the lowest energy conformation will always be a staggered conformation, and there's no reason to think that this one would okay, I use the term loosely, but choose to be in an eclipsed conformation. That would be silly. So we got this, and so now if I look down this part of the Newman projection, which I should have drawn out before, but that's okay. Okay, I'll just very quickly draw a really bad Newman projection. Oh yes. Yes, that's very bad. Good. Okay, so now looking at it this way, I've got the bromine over here. I've got my CH3 group over here, and the hydrogen is up top. And then on the black carbon back here, I've got the chlorine up in this corner, and then the other two are hydrogens. Right? Okay, so that's approximately what that should look like. And if I'm not being too presumptuous, which I don't think I am, that's correct. That looks like. Okay. So I'm not going to go through the whole process for this third one over here, but I will make note that this one is very slightly more complex, and that's because at least it can look more complex because it's not just two carbons and you know the atoms that are attached to them. Now there's a whole entire ethyl group here, and so I'll just quickly show you how we represent that. So what I'm going to do is do a red eye. Okay, so we're going to be looking at it from this perspective. So once again, the red carbon is in front, and the black carbon is behind. Okay. And so for this one, we have got hydrogen here, hydrogen here. What do we got in the back? We've got chlorine up here, hydrogen here, and methyl group here. All right. Now, what we do with this. So for this group up here, we just call this a CH3 group, which is what I've very messily done down here, because that's all it is. It's just a methyl group on the end of that bond, and this here is an ethyl group. So how we say that is we go CH2 CH3. So we abbreviate the ethyl group by just writing CH2 CH3, right? Because this is things are getting too crowded in here. Just a moment. So this one is CH2, and this one is CH3. And so we just kind of combine those together into one kind of substituent because we're looking at this bond specifically. So yeah, it looks a little harder, but really it's just doing the exact same thing again. Same logic, same reasoning, all that. Okay. Alright, so focusing on the C2 to C3 bond of 2,3-dimethylbutane. Draw Newman projections for all possible staggered and eclipse conformations. Rank the compounds in order of increasing stability. Okay, so the first thing that we need to do with this is we need to know what 2,3-dimethylbutane looks like. So, we're going to use the skills that we've been working on. Funny how that works together. All right, so the principal carbon chain is a butane. So again, butane will have 4 carbons, and because it ends in ane, it's an alkane, which means that they are all carbon single bonds, carbon-carbon single bonds. So there's no double bonds, no triple bonds, no rings, no nothing. I should say there's no ring. We know that there's no rings because if there's a ring, it would have to say cyclo in there somewhere, but this does not. So butane being just 1, 2, 3, 4 carbons, and for this, it does not matter which way you number it from. It will be the same either way. 1, 2, 3, and 4. Cyclo like cycles. Yes, exactly. Yeah, so like we could have things like this, which is if these are all single bonds, then this is so there's 6 points on this ring. So it'd be hex. They are all single bonds, so it'd be ane. So hexane. But these are in a ring. So this is not just hexane, this is cyclohexane. So that's a really important part of the name to indicate that there are 6 carbons in the ring. Yeah, oh yeah. So we could also. So that's a little bit different from, for example, this. So we've been over this before. This is benzene. And benzene is the proper name for it. It's, well, that's mostly true. It is, benzene is not a systematic name, but it is, the completely ubiquitous name for this molecule that everybody has used for centuries, and it is just not likely to change soon. But for benzene, but really we do that because it's special, because it's just such an important molecule that it essentially has got its own system of categorization. Which, again, it's not systematic. It's an archaic way of naming it, but it would be kind of silly for me to like teach what the systematic name of that is. Well, I wonder if that's true. Well, okay. I have to actually think about what I'm going to do here, so we could generate a systematic name for it. Mazel. Okay. Okay. And see, this is what happens when you do absolutely no prep, and you have a neurospicy brain that just wants to go in every direction at once. So it takes me a minute to decide what I actually want to do. Okay, so let's forget the name benzene. Let's pretend that we are not living in like this, I don't know, 16 or 1700s when stuff like this got named. And nobody could nobody had an agreed upon way of naming these things. I took a course in my undergrad called A History of Chemistry. Fantastic course. We went all the way from like the kind of like ancient Greeks kind of dabbling in something that would become chemistry, all the way through alchemy. And then towards what modern chemistry actually is, and we learned about like how a lot of these really archaic names came to be. If I recall, benzene wasn't one of them. But okay, so this, so it's got the same structure as cyclohexane, but it has some multiple bonds in there. Oh yes, it was a very cool course, taught by a person I really enjoyed, and it was not really aimed at science majors. So it wasn't like any kind of a difficult science course. It was much more based on just like the history of it and personal interpretations of it. But it was very good. It was very, very fun. So we would again call this hex, because the skeleton of this is made up of, once again, 6 carbons. And because those 6 carbons are in a ring, we again have to say it is cyclohex. But this is not a case where we have all carbon-carbon single bonds, so it does not end in ane. It does not. It is not an alkane. This ends in. So this has 3 double bonds, and double bonds means that we're looking at an alkene. And just once again for reference, we've got alkane, we've got alkene, and also alkyne. And so this just means that, an alkane means that the highest bond order is 1, which is to say that they're all single bonds. Single bonds have a bond order of 1, generally. An alkene means that the highest bond order is 2. So there's at least one carbon-carbon bond that has a bond order of 2 or is a double bond. And as you may have already guessed, alkyne means that the highest bond order is 3. So there is somewhere in there a triple bond. Now, in the case of benzene, the highest bond order is a double bond. So it's the highest bond order is 2. So it is a alkene. Now the thing with naming this is that we have to be specific as to which carbons have the double bonds. And when we are naming alkenes, so on this structure, it doesn't matter where we start because every carbon is part of one of these double bonds. So we could let's just start here. 1, 2, 3, 4, 5, and 6. So we have to specify which carbons the single bonds are on. So we would say, well, actually, so I believe that the proper way to specify those is hex dash 1, 3, 5 dash ene, right? Because dashes separate letters and numbers, and commas separate multiple numbers. So this is saying that there are 6 carbons in a ring, and carbons 1, 3, and 5 are the first carbons in a double bond. So yeah, carbon 1 is here, and then we go over here, and then the second double bond starts at carbon 3, and then the third double bond going in this direction starts at carbon 5. So that's why we name it this way. Also of critical importance here is that we must number it this way. It doesn't make any difference which carbon you start from, but it matters which direction you go, because if we started again like this carbon is going to be carbon 1, you cannot number it counterclockwise. This is not carbon 2, because when you are numbering these based on like starting on a double bond, carbon 1 must be the start of the double bond, and carbon 2 must be the other end of that double bond. So we started on this carbon, which is on this double bond. And so once we've decided this is where we're starting, then our direction is decided for us. We must go this way because that's the direction that the double bond goes. And that's how we get this. So this is the systematic name of benzene. Alrighty. Okay, so let's keep going over here. So we're almost done over here. So we've got our numbering down, and so, but this is 2,3-dimethylbutane, which means that on carbon 2 there is one methyl group, and on carbon 3 there is one methyl group. And that's it. This is 2,3-dimethylbutane. And so we are focusing on the C2 to C3 bond and creating a Newman projection from that. So that was not a bright color. So we're going to change it to this one. Okay, so this is the carbon 2 to carbon 3 bond. And so we're going to pretend that we're looking this way. Okay, so what we need to do here is we need to we need to be specific as to what is connected to like what are the substituents on carbons 2 and 3. So carbon 2, I just want to take these out. Oh, I've done it now. Okay, I'm just going to redraw this whole thing because that'll be easier. Okay, so, yeah, again, this is carbon 2, this is carbon 3. So, when you're drawing tetrahedral carbons, which is, say, carbons that have 4 single bonds, which all of these are, dimethylbutane, all single bonds. You must have 2 bonds. Well, I should say, the easiest way to draw this, that will break your brain the least, is you need 2 bonds that are in the plane of the screen or the paper or what have you. And we've already got that here by having just drawn this skeleton. So you need 2 bonds in the plane of the screen. You need 1 bond on a you need 1 dashed bond, and you need 1 wedge bond. Like that. Okay, and similarly for carbon 3, get a little closer. So again, we've got two bonds in the plane of the screen. We've got a dash bond, and we've got a wedge bond. Once again, carbon 2 has a methyl group on it, and that's all that was specified. But that only counts for 3 of the bonds, right? So there's a carbon here, there's a carbon here, and there's a methyl group here. So this last one must, by default, be a hydrogen. And very similarly, or some even might say the exact same as that is for carbon 3. We've got carbon here, we've got a carbon here, we've got a methyl group here, and then we must have a hydrogen here. So I'm going to say carbon 2 is red, carbon 3 is blue. So, because my perspective is coming from over here, so we're going to draw carbon 2 in front and carbon 3 behind. And then I'm not going to go through the entire process again, so pretending that we're looking from this perspective. So the hydrogen is coming out of the screen towards me, which if I was looking at it from that angle would be on the right side. So I've drawn this a little wonky, and I want to make it better. Apologies. Okay, this will make slightly more sense in my brain. Okay, so still red carbon in front, blue carbon behind. I've just turned it upside down because that's kind of how I drew the substituents, and that's what makes better sense to me. So, from the angle that I've drawn the eye, the hydrogen would be going off to the right. And so we draw that one up here. The methyl group is going away from me, like, so out of the screen that way. And so that would be to the left of that eyeball. And so that's over here. And then the in-plane substituent is also a methyl group. Okay, and so for the blue carbon, the in-plane carbon is a methyl group. Methyl group. Going from that, wow. Going from that direction, the methyl group is going away from me, so to the left of that eyeball. So that would be over here. And then the last substituent is a hydrogen. Alright. Okay. Okay, so it says draw Newman projections for all possible staggered and eclipsed conformations. I'm just deciding whether I want to actually do that or not. Yeah, maybe we'll do a couple at least. So the easiest way to generate all of the possible Newman projections is you just pick one of the carbons. It doesn't matter which one, and just pretend that it rotates by 60 degrees. Now, up here. No, I did not keep those drawings. But one thing I mentioned last time was when we were going from staggered conformation to another staggered conformation, we rotated these groups by 120 degrees. So this methyl group would end up where this one is now. This methyl group ends up where that hydrogen is, and this hydrogen moves over here. So that is to get from staggered conformation to another staggered conformation. But we are trying to draw all of the staggered and eclipsed conformations, so we're only going to go by increments of 60 degrees. But once again, it's exactly the same process. Is that all you have to do is rotate, like pick one of these carbons to rotate, and just rotate all of those groups by 60 degrees. So this methyl group is going to overlap with this methyl group. This methyl group is going to overlap with the hydrogen, and this hydrogen is going to overlap with that methyl group. Gorgeous. Oop. That wasn't drawn right. Okay. And so when you're drawing these in eclipsed conformation, obviously it does no good to draw them literally on top of each other. That's just not practical. So you just draw them slightly offset from each other, and that's kind of just like understood to be like perfectly lined up with each other. That would be a true eclipsed conformation. Would be those bonds being perfectly lined up. It's just not easy to do that on a 2D plane. Some might say impossible, and they're right. So, so the groups on the blue carbon have stayed stationary, so those don't change. This is still a methyl group. This is still a methyl group, and this is still a hydrogen. But now it's the red carbon that rotated. So this one leads to, I'm going to put these in a different color. So, gross. H3. This one is a hydrogen, and this one is a methyl group. Okay, so that is how we do. So this is a 60-degree rotation of the red carbon, which is taking it from a staggered conformation to an eclipsed conformation. Yeah, so I have decided I do not feel like writing out all of these Newman projections, because I'm tired, and I would like to wrap this up fairly soon. But let's just imagine that I did, and then we rank them based on their stability. And again, the another way of putting this is rank them in terms of like what is the energy of this compound. Because everything wants to be in the lowest possible energy, the lowest energy state, where the electrons are as spread out as possible. And this is always going to be a staggered conformation. Is going to be the most spread out. It is going to be the lowest energy. It is going to be the most stable. And then you just do what we did last week. Was we counted up the interactions of the large groups, right? Because but why do they want to be at the lowest energy? Make room for external stuff? No, not exactly. What I mean by lowest energy is that we have, as much as possible, we have minimized electron-electron repulsion. So think of it this way. Electrons carry a negative charge. So if you get two electrons close to each other, like charges repel each other. So two negative charges, if you bring them close to each other, they are unhappy about this, and they will actively work to rectify the situation. They would like to get further apart, because they share the same charge, and they'll repel each other. So think of magnets. If you take two magnets where you've got a north pole and a south pole, you take two north poles, and they will repel each other, and try to get them close to each other. And as you do this, as you get them closer and closer to each other, they will exert a force on you to try and get further apart. And this is kind of the same thing that's happening with electron-electron repulsion. Is you can force them to be close together, but it requires energy input from you in order to push these together. And so you have put energy into this system, and so you can say the system of these two north poles of these magnets is now higher in energy. That is okay. Don't you worry about it at all. So they repel each other just because opposite charges attract each other, and same charges repel each other. So this is just kind of axiomatic. It's just kind of it's sort of just a given in in physics is that if you have two charges of the same sign, they would like to not be together. It's like protons and electrons attract each other. Electrons and electrons repel each other. Just like north and south poles on a magnet will attract each other, but north and north poles on a magnet will repel each other. Same thing. So when we say that, is there a reason for it, or does it just like happen? So I mean, there is a reason for it. I don't think I understand it well enough to explain it well to you. So this is this is stuff from like my like second year physics course. I really like physics. I just am not that good at it. So yeah, like this is like there's reasons for this that somebody who's really good at physics could explain well. For me, I don't think that I have the brain power and expertise to explain this well, but yeah, thanks. Yeah, I really try hard not to just like go past the edge of my knowledge, because I really don't want to say something that is just fully incorrect. Yeah, that's always a little anxiety of mine, but yeah. So just kind of for now, like by all means, look up a better explanation of this from somebody who's so much smarter than me. But like you definitely can observe this effect for yourself, by just like if you've got like horseshoe magnets or just like just magnets, then in one orientation they will attract each other, and like you'll have to exert a force to pull them apart. But in the opposite orientation, they will repel each other, and you'll have to exert a force in order to get them closer together. So this is what I'm saying when I say like this molecule is in its lowest energy conformation. So like putting it in a higher energy conformation, like the I can just say higher E. E is for energy. And then this one is lower E. Okay, so in order to have this, hello my dude, how you doing? Is my puppy. Hi. Oh, I'm just having a snooze. That's okay. Okay, so in order to take this molecule from its lower energy state to its higher energy one, so overlapping these substituents more completely, getting the electrons closer to each other. That is like taking those two north poles of the magnet and like trying to force them together. So the energy to get the magnets closer to each other comes from you. You're putting the energy into this. And so that system is being made higher in energy because of that. And so that's what I mean when I say this is higher in energy. It's because there's some energy input from its surroundings that is required to go from the lower energy conformation to the higher one. Let me know if that makes sense to you, because I am more than happy to try to find another way to put it. Sports car needs more gas to power. I think I could get behind that. I like at the very least I see what you're getting at, and I do not think that that's wrong. AA versus AAA batteries. I I think the analogy is getting a bit strained there. Um, but oh no, that's okay. Don't worry about it. Um, oh god, I. Oh, I am actively resisting going down a big rabbit trail because that rabbit trail is deep. Because I do have a reasonable understanding of how batteries work. Yes, that's the one. Yes, very, very much like an activation energy. And in fact, you could absolutely say that going from a staggered confirmation to an eclipsed confirmation requires an activation energy, and it looks exactly like the energy diagrams that we drew before. So yes, I'm so proud of you for getting to there. Yes, exactly that. Um, yeah, that's how it do. Because activation energy in chemical reactions, like it works the same way. You require a certain amount of energy to make things either get closer together than they would prefer to be, or to dissociate certain things. So yes, that's perfect. Hell yeah. No, yeah, you did so good. Soak it up, live it up. You did great. Um, yes, exactly that. Yeah, activation energy. I should remember to mention that that's the same operation. Yeah, yeah, totally. Um, yeah, that's some stuff I had to go over in the last paper I published when we were going over the conformational studies of these things, and like we did tons of computational work to calculate the energy that it requires for my compounds to rotate and adopt different conformations. So yes, perfect. Yes, very good. Okay. Um, yeah, so again, ranking them in order of increasing stability. I'm not going to super bother with that. Just eclipse confirmations are always higher energy than staggered confirmations for all intents and purposes. Still haven't read them yet because I've been doing so many things. We'll do after the stream. Oh, don't you worry. No rush at all. Yeah, I'd be and oh yeah, and I was going to mention because we were talking about this last time. And you're saying like you like to read some papers even if you don't understand it, and I absolutely love that. I really, really do. um, and it shows me a curious mind, and I love that. um, but like and I think I mentioned then, like, don't worry if you don't understand it all. Like I read lots of papers, and very rarely do I feel like I fully understand what they've done and what they're getting at, because it is simply not possible to be an expert in everything. I'm very good at my little corner of chemistry, but there's lots of people doing lots of stuff. So yeah, super. Don't worry about it if you don't get everything in a paper. That's all right. And like some of the best things to take from papers like that are just like look at the very end of the paper, because there's pretty much always going to be a conclusion section. Certain types of articles, certain formats don't require conclusions, but most of them will have a little section of conclusions. And so like give it a read as much as you can, and then look at the conclusions and see what the authors have said about their work, and what kind of their takeaways from this work, because they should be giving a little bit of an indication as like, here's what we get from this. Because like one of my favorite teachers always told me, like, gave me advice with writing, and it's like, first you tell them what you're going to tell them, and then you tell them, and then you tell them what you told them. So the introduction and the conclusions are typically like the easiest, best like summaries of what a paper is about. Sometimes put it into ChatGPT, say explain to me like I'm five, and it's a little helpful. That's yeah, no, that's that. I think that's a great method as well. I just oh man, yeah, I'm still getting kind of like accustomed to AI like ChatGPT being a thing because I'm old and set in my ways. But yeah, that's a great tool to use, and I love that you're doing that. Yeah, yeah, no, the intro and conclusions. Yeah, if you read nothing else in a paper, read those. But read everything else too. It's fine. Hello, love. How you doing? Is your tummy feeling okay? Doing all right? Hi. Ba-dum-bum-bum. Hello, sweetie. Do you need some water? You can have some. I mean, your fountain is right there, but ChatGPT is wrong and right similarly as Google. It's really interesting too how it works differently. Yeah, yeah. I've definitely I've used ChatGPT somewhat, and another one called Perplexity. And could you stop chewing on my carbon? Thank you. So yeah, I have used some of them. I have used them to like talk about some stuff, and they're right a pretty good amount of the time. But yeah, sometimes they go down a weird trail, and it's like no, that's very very wrong. Um, what's weird too is it gets data from accounts on Twitter and socials too. Oh yeah. So one that I like a little bit more than ChatGPT is called Perplexity. So it's just like, yeah, I got it. Hold on, just a second. So I like Perplexity. I think it's a little bit less sophisticated than ChatGPT, but what I really like about it is Perplexity will always cite its sources. So it'll get, and you can just like click into the links that it provides to its sources and see where it got this information from. And so that's a really really good, really important thing, I think, for these chatbots. Yeah. That's one reason I use Perplexity more than I use ChatGPT, precisely because of that. Because sources are just they're so important, and yeah, like if they're taking information from like social media and stuff, it's like okay, that's super, but I can't cite that in my paper. Oh my god, which brings to mind one of the funniest things that I have ever seen in all my years of teaching. Was there's a report where one of my students like I always talk to my students about when they're writing reports and the importance of citing good sources. And then I go over with them like, oh, here's what a good source is. And like, there's really good sources on the web, but you need to be you need to think critically when you're looking this up, especially on just a web page. And so it confuses celebrities or entertainment people with random accounts of Twitter. Oh, that's funny. Yeah. ChatGPT could use a little bit of critical thinking skills too. But yeah, so one student, I okay, fine. Eat my carbon. It's fine. So one of my students answered one of the questions in their report, and the answer was just it was really wrong, and so this was like a bit of a red flag to me because I'm like, okay, why? What? Do you want to get to your fountain? Because you can. I can move this. So gave me a really wrong answer, but like had a citation, and so I'm like, okay, so where on earth are you getting your citation from, and ending up so wrong? And what they cited was Yahoo Answers. So just like a public question board. And so I took the time, like a good couple, like a good minute of my day to type out this entire URL and look up this Yahoo answer. And it was just some random schmuck on the internet just answered a chemistry question extremely wrong. And my student in organic chemistry, it was like second year undergrad, uh, just just gave this incredibly wrong answer based on some person on the internet. Just assumed that the internet level, like core vibes. Yes, exactly that. Um, and I just, oh man, ugh. Half of what I love about teaching is just the wild stories that you get, and like certain pieces of feedback have had to give students, like you did not create a nuclear reaction in your flask. Um, just yeah, weird answers that you get sometimes. Um, yeah. So in academia, what's Wikipedia? Okay. There is a ton of really good information on Wikipedia, and I genuinely use Wikipedia in my research sometimes. But what I will never ever do, and what I have told my students to never ever do, is you don't ever cite Wikipedia in your references. And the reason is because anybody can edit Wikipedia, and so you absolutely must not use it as an authoritative source. However, one great thing about Wikipedia is they're very good at listing their references. So, by all means, use Wikipedia because there's tons of good information and it's very, very useful. But follow the sources that the Wikipedia article cites. Make sure that it says what the Wikipedia article says that it does, and then cite that. So, use Wikipedia. You have my blessing, my encouragement. Just, it should never show up in your list of references. Yeah. It's a great place to find sources. That's what Wikipedia is. Yeah, absolutely. And I'm not kidding. Like this, Wikipedia is genuinely helpful sometimes in just like doing fundamental research. Yeah, it's really good for that. It's just you always have to maintain some critical thought and like just always keep in mind that anybody can edit these, and like maybe it'll get caught and corrected, and maybe it'll stay in the article for years and just be wrong. So yeah, follow the sources, and like use that to find a primary source that you can cite. That's my advice there. All right. So with that, so yeah, the last question here is really just exactly the same thing that we've been doing. Yeah, so I don't think I'm going to go over that one because I am just about spent for tonight. And that is the end of this problem set. So on Friday, I'll be starting a whole new problem set. I've got one picked out already. We'll be talking about some actual chemical reactions and going through mechanisms, and so doing a lot of arrow pushing, seeing how electrons move and react, and once again, we're going to find that that all of these reactions that we're going to be doing, they end up spreading out the electron density as much as possible, reducing that electron repulsion, and making more stable products, lower energy products. So yeah, I'm looking forward to that. It's this stuff is fine. The naming, the drawing, it's all very important fundamental skills, and so I wanted to spend time on it and like really get some of the groundwork laid. and but then we'll start getting into some more dynamic stuff, I guess. Okay, so great stream. So thank you so much. Always appreciate you hanging out. So does it go lower than the ground state, or is the absolute lowest the ground state? So the term ground state is it becomes kind of difficult to apply when we're talking about intermolecular reactions. So reactions between more than one molecule. And so you can have you can have two molecules that are individually in their lowest energy states. But when they are brought together and they collide in a certain way, as long as they're able to clear that activation energy, get over that barrier, then they can rearrange bonds, they can form new compounds, which overall have a lower energy than it started with. And we can go the other direction too and end up with stuff that's higher in energy than we started with. But like, so all this to say, the term ground
Mic
state
on, mic off.
is difficult to apply to some of these things, because like, yeah, they're in their kind of lowest energy state that they'll tend to occupy. But if we change this and modify this thing, then this one might be in a quote unquote ground state that is lower than the reactants. So products might end up lower in energy than your reactants, but like one of the molecules might go up in energy, and like its new ground state might be higher in energy than it started. But overall, the whole system will be low. It becomes a bit of a complicated mess. So using terms like ground state works really well when we're talking about, one molecule, or like even like one atom, like a hydrogen atom in its ground state. Those are easy to talk about. But once we get into reactions and we have like, every possible permutation of how these things could interact and rearrange themselves, then ground state kind of becomes not necessarily the best way to think about these things. We'll sometimes talk about lower and higher in energy, but honestly, even then, that can be kind of deceiving, because once you get into these kinds of paradigms that make use of kind of the more like the somewhat more complicated thermodynamics, then there's different ways that will end up talking about them that are just easier to work with than like ground state or excited state, because it doesn't super apply to the systems we're going to be working with. But I will definitely do my best to explain that as simply as I can when we get into it. I'm hoping it'll make more sense once we get going. But yeah, so I guess my answer to that is sorta, not really, maybe kinda. Hard to say, but we'll get into that on Friday, and yeah, hopefully that'll clear things up a bit once we start working on it. And like a lot of these things, like they're hard to talk about in words. But it's easier once you get into like actually drawing stuff and think about, okay, well, why does this happen, and what makes this structure like more energetically favorable than that one, and so on and so forth. So, yeah. Oh man, just occurring to me that I might have to give just the briefest of primers on the thermodynamics of these molecules, and like what makes them fundamentally lower in energy than something else. But yeah. Yeah, no, I got, and I mean, like at the end of the day, like I've told, hundreds of students by this time. Chemistry's hard. Like this stuff is not trivial. And the biggest thing about it, I think, is chemistry is not intuitive. It isn't. There is no such thing as just like having a common sense for chemistry, because you frankly don't have one, because like we do not interact with chemistry on this level in the normal course of our lives. So we have to like we not with our at least like not with the senses that we use to assess the world in most other situations. Like we have to use instruments to collect data that we then interpret as like, okay, so this has happened and this is why. And by doing this, like by studying this stuff and learning these processes and building up our procedural knowledge of how these things work, that is how we like construct a common sense for chemistry. But yeah, like if it doesn't make sense to you sometimes, if it just like seems weird, that's okay. Like that everybody goes through this, because nobody starts out having a common sense for what happens in chemistry. It must be learned. There's no other way. But yeah, so looking forward to getting into that bit on Friday. And yeah, I hope you have just a lovely night and a great week, and I'll hopefully see you then. Okay, bye.